Jorge Cortes. I know Jorge since I started my PhD, so it's an extreme pleasure to have him here as a faculty of the University of Michigan and with the history that we have. So, typically, when I introduce speakers, I don't use the phone, but Jorge is an exception because, the bio is on the left side and has like a variety of information. So, Jorge, first of all, he is a professor at the Mechanical and Aerospace Department at the University of San Diego. This I remember, and I can say it by itself. And he holds there the Cymer Corporation and Chair in high-performance dynamic systems modeling and control. Now, beyond that, he has written 2 books. The one book is on geometric control and numerical aspects of non-holonomic systems, as well a book that is more relevant to the research that I do with my students, which is distributed control of robotic networks. And one of the reasons that I was in love with his research when I was undergraduate, and then I decided when I became a PhD. So he's a fellow of IEEE, SciAm, and IFAC. He has co-authored many papers right now, and several of them, tens of them, they have best paper awards. For example, some of the most recent 2021 IEEE Control Systems Outstanding Paper Award, 2012 ACC Best Paper Award, also known as O. Hugo Stack Best Paper Award in the theory category, 2019 and 2023 IEEE Transactions on Control of Networks Systems Outstanding Paper Award. He has done a lot of distinguished service, so I will close and I will leave the podium to him with his research interests, which are diverse. So they include distributed control and optimization, network science and complex systems, software control and coordination, distributed decision-making and autonomy, network neuroscience, and multi-agent control of the robotic power and transportation network. So let's welcome Jorge and Jeff.
Thank you, for the very nice intro. Thank you for giving me the chance to experience Michigan weather.
You chose the 76.
I thank you for lending me the computer because I had a little trouble with water and my computer, so now I'm using Brazilian. So, yeah, today I'm going to talk about control. You can think of it, this is the control seminar, right? So there are definitely connections with systems and control, but the problem or the motivation is more related to optimization, but you'll see that the two are sort of intertwined the way I talk about them. And before I start, I should acknowledge my student, which of course did all the work. Ahmed Aliboy, he is now a postdoc at UC Riverside. And from the title of the thesis, you see that he kind of had like a broad variety of interests, but I guess about half of his thesis, or maybe a little bit more, was the work that I'm describing here today. Okay, so I have a few slides just to sort of explain what was our motivation, to fall into this safe gradient flow that you saw in the title, and this is definitely control driven. So what do we like typically? We have our plant, we have our state, we have our dynamics, we have our input, and we want to design a controller, right? A controller to do something, And we have many objectives in mind. Maybe it could be a stabilization, maybe it could be some sort of, maybe the plant is already stable, but we want to optimize performance, right? Or set points, or maybe we want to provide robustness, to the plant. And usually when we do that, then we have lots of constraints. Well, usually to begin with, the plant is typically nonlinear, so that's difficult to do, right? Because the nonlinearity makes it difficult to even design a controller that makes any of these happen. Sometimes we have limitations on what we can do, in terms of the actuation effort. Sometimes we have physical constraints on the plant, or maybe all of that. So one way of sort of hiding all that complexity, as to how do I design the controller, is to, set it up like that, right? Here I just gave you the control, that will achieve something, or I just gave you a way to design a controller, right? And it's an optimization-based controller, And basically I'll kind of encode my objectives, hopefully in the J, right? In the objective function that I'm going to try to optimize. I'll encode my constraints, right, on the constraints, on that optimization, that set, no? And then I will say, okay, just solve that optimization and use that controller, right? So all of a sudden it looks like the complexity is gone, but it's not, right? We just, put it under the rack, right? It's all in that J and that constraints. And but if you think about it, we do that a lot, no? And so many of the techniques that we use in control, like model predictive control, for instance, right, is really a form of, encoding things, no, into objectives, constraints, and using that controller, right? So model predictive control, extreme seeking, online feedback optimization, even here, I know many of you work on CBFs, right? So these optimization-based controllers, well, those are a particular instance, right? But I just. So, well, okay. Now, going back, hopefully that was not me. Okay. So going back to the hiding the complexity, no, then, well, now you see at least that there are two processes here, right? Like I have the plant and I have to solve this optimization, right? So that I feed that controller in here, no? But maybe these two things, it's not like this can wait for this, right? Like you will have some way of solving this optimization and feed it here, but usually solving an optimization problem itself is a dynamics, right? It's an algorithm, right? And so, well, you can, like for instance, in CBF control, this is usually a QP, right? And so we say, well, a QP is fast, no? Or sometimes I can even find it in closed form, right? And I will just implement it or something like this. But, generically, well, the time scales of how are you solving these two things matter, right? So I guess we are interested in actually embracing that, right? And saying, well, I'm going to try to solve this optimization problem, and I'm going to, feed what I get into that thing. But I'm going to account for the fact that, maybe I don't have even the right information about the plant, right? I need to, be aware of the fact that these two processes might be running at different time scales. No, and the interesting thing is that when you are solving this not in an offline fashion, right, where I solve this and I use, but sort of you really look at this as an interconnected dynamical system, and you kind of something that could happen when you do it offline is that by the time you use the controller that you have here on the plan, then the plan is somewhere else, right? No, because it takes time to do this. No? And instead, you are kind of doing it at the same time, accounting for the different time scales. Well, that at least you have a chance of addressing that, right? So, I guess all of this is just to say, I'm just going to look at whatever solver I have here as a dynamical system itself, right? And I'm just going to look at these two things as an interconnected dynamical system. Okay? And then the one thing is that now what I want to design, and this is kind of the motivation for what is coming next, right? Is because I know that what is coming from here is subject to constraints, right? Remember, it was an optimization problem with constraints. I want to be feeding to the plant always, right, things that satisfy those constraints, right? Because this might not necessarily have converged to the optimizer yet, but I definitely has to satisfy the constraints, right? Because, the constraints were encoding maybe physical constraints, maybe. Okay, so this idea of designing dynamics, right, that solve optimization problems, no? I guess now, I'm going to just focus on this, no? I'm actually going to forget even about the plan, right? I'm just going to focus on this side, and then eventually, I guess, I'll come back. So this idea of having dynamical systems that solve optimization problems, it goes back, to so I guess even you can think of gradient descent, right, as a dynamical system that solves unconstrained optimization, right? When you want to optimize a function, what do? You follow the gradient, right? Down or up, no? Depending on what you want to do. And so that goes back to Cauchy, rediscovered by Hadamard, and the convergence properties that eventually converge to a critical point and minimize it if the function is convex. No, that not more recent if you think about it. Maybe you are also familiar with primal dual or saddle point dynamics, this idea that when you are trying to constraint optimization, you follow the minus the gradient in the primal dual and plus gradient in the Lagrange multipliers, right? And that again goes back to the economics literature in the 50s. Samuelson was a Nobel Prize winner, and he has some simple counterexamples, right, where that dynamics does or does not converge, right? Those kind of things. And now closer, I guess, to our community, Brockett and that nice book by Helm Moore, right? This idea of algorithms that compute eigenvalues, that order vectors, right? And do things like that. And systems that solve problems in linear. So that was the motivation, but I'm gonna forget about the plant and everything, right? So a word of caution, this X now is really the U, right? Because I'm trying to solve the optimization problem, right, for the controller. But okay, who cares? This is an optimization problem, right? So if you wanna solve an optimization problem, what do we typically, unconstrained like this one, what do we typically do? Well, I guess gradient, descent either in discrete or continuous time, either or. And we like it because, well, many reasons, it's easy to prove convergence. We have a Lyapunov function or a Lassalle function right there, which is the cost function. We know, first order methods are easy to implement. They scale up well. They are robust to noise, or I mean, they are slowish, right? But, they have all these nice properties. Yeah, they are robust, right, to noise and so in constraint instead of optimization, which is the one that we are interested in, right? So I guess I'm writing a generic optimization problem now, objective function, inequality, and equality constraints, right? Very generic. I'm not assuming yet anything about convexity or anything, right? Just these generic things, right? So we have what we call the feasible set, which is the set of points that satisfies the constraints, and essentially what you want to do is minimize this function over that set, right? That's really what you want to do. So what we want, I guess, inspired by the motivation that I was mentioning to you before is, yeah, we want to find a local minimizer, with our algorithm, or at least a little that, right? Well, when we start making global convexity assumptions, this will be global, but okay, at least a local minimizer. And then we want an anytime algorithm, right? And by anytime, I mean this idea that, if I start feasible, I remain feasible, Why? Because of the motivation that I mentioned to you before, right? Because I might be providing this to some other layer, right? That needs these constraints to be satisfied. And I don't know when I'm going to pull back this information, right? So I need to be able to implement it. Okay, so how do we actually do that? I mean, many methods, right? The one that you might be familiar with is projected gradient descent, in this case, right? Where you just basically follow the gradient, while you are in the constraint set or in the feasible set. And then when you hit the boundary, if you hit the boundary, right? But if you hit the boundary, right, you project to make it tangential, right? So that you don't leave. And so this is, does convert to local minimizers, makes the feasible set invariant, but it's discontinuous, because you don't care, all of a sudden you care, right? And so you do this thing. Saddle pod dynamics that I was mentioning before, right? Where you follow that's another way of solving these problems, right? Minus the gradient, in the primal, plus the gradient in the dual, right? With, okay, some projection because the Lagrange multipliers must be positive. So still convergence to local minimizers now is not discontinuous, but it's definitely not a normal invariant, right? If you are, if you've used them, they are typically oscillatory kind of convergence, right? They sort of oscillate, so you go all over the place, right? Until you converge. Asymptotically, you satisfy the constraints, but asymptotically, right? Not while you are executing the dynamics. We use in optimization, we use penalty and barrier methods, and they have these two nice properties, but typically you give up exact convergence, right? Because the penalty or the barrier actually does modify the objective, right? So you converge close, but not to the actual optimizer. So if we want to have all three, well, that's what we try to do. And so, okay, so here is the basic idea of our design, right? In this example, I think I'm plotting the level sets of the objective function, right? So if you try to optimize, you are just going to go orthogonally, right, to those level sets, right? And in green, you see the constraint set, right? So I'm supposed to stay here, right? So for instance, what will projected gradient descent do? Well, it will just, orthogonally until it hits a point here in the boundary, then it will project, right? And then it will reach the optimizer, right? That's what. I think maybe this is what I drew here, right? Yeah, exactly. So, I mean, if you just follow the gradient, you will just do this, hit the boundary, and then get here, right? And so, I mean, on the one hand, because I want to optimize the function, following the gradient is the right thing to do, I mean, first order dynamics, the right thing to do is the direction of deepest descent, right? And I guess that's what we want to do, keep optimizing the function unless we need to worry about the constraints, Exactly. So instead, what we could do, right, so that we don't, step outside, and this is the way we think about this, right? Is like, I'm gonna the gradient of the g, right? G is the function that is defined in the boundary, right? The constraint set, So the gradient is sort of pointing like this, right? Something like that. So I'm gonna look at these dynamics as actually like a control system, right? This is the drift. This is my control input. Well, this is my control input, but this is my vector field, right? My control vector field, right? And if I do u equal to 0, I'm just following the gradient, And the thing is that I'm only gonna use this to remain safe, That's kind of the. So if you are familiar with CBFs, that makes perfect sense, right? I have a control affine system, and I'm just gonna use the u to make the system safe. So that's literally what we do. Yeah, exactly. I guess you could look at projected gradient descent as an extreme case of this, where I don't do anything until I am at the boundary, right? And when I am at the boundary, then I do something, right, to do something like that. Instead, in safety critical control, in CBFs, what you will do is you will do something gradually, right? As you are getting closer and closer, you will, like what you see, the trajectory that you see described there, you will do something like this. So in general, that's what we do, right? We say, okay, that was for one constraint, right? But in general, you have, I don't know, M inequality constraints, K equality constraints, right? And I'm gonna, use inputs for each one of them, And literally, what I have is, well, this is what I want to be doing, right? Nothing of this, right? I just want to be following the gradient, but I want the algorithm to be anytime, so I want to remain. So I'm going to choose these U's and V's, in a way that make the system safe. That's really what I'm going to do. Yeah, exactly. Enforce feasibility of the corresponding constraint. So we think of U and V as inputs, to the system, and then we are going to design a feedback controller that enforces, feasibility, which enforces safety, I guess, of the feasible set, right? Yeah, exactly. So, okay, I think I'm going to skip this because you all know about CBFs, right? That's basically the idea. I mean, you have it here. I guess I have a bunch of CBFs. This is like a component-wise inequality and a component-wise equality because I have multiple constraints, right? But you all know this idea where this gradual, worrying about the boundary that I was mentioning, right? It's kind of driven by this thing over here, right? So when you are when you are inside in the set, the G is going to be negative, right? So this thing is going to be positive, right? So you are letting G dot be less or equal than some positive quantity. So G dot can be negative, so, deeper into the set, or it can actually be positive up to some bound, meaning that, you need to get closer to the boundary, you will get closer to the boundary. When you are right at the boundary, this will be 0, right? And so G dot less or equal than 0 means, don't leave, right? Stay, inside. But you see that this is gradual, right? Like, as we get closer and closer to the boundary, this gets closer and closer to 0. So this positive quantity becomes smaller and smaller all the way to becoming 0, right? And actually, yeah, that alpha guides, how scared or not scared you are from the boundary, right? From being close to the boundary, Because if the alpha is very, very large, right? It means that even if you are very close, this is still very large, right? Because the alpha is large, right? So it's like you're not very scared of the boundary, right? The alpha is very, very small, is that you are very worried, right? Like, even if still you are far, right? But you are still, don't get too close too fast, right? So that's a design parameter, that you can play with. And so this is the way we approach the problem. We say, okay, we have a control system now, no, that's going to be my dynamics. And all the controllers that make, or the controls, right, that make the feasible set safe are the ones that make these two things true, right? And this I can write, no, this G dot is just the gradient of G times X dot, right, over there, no? And this X dot is the same thing, no? So you can expand those things, no? And they look like that. And, you know, it's harmful, but the important thing to notice here is that everything is linear in U and B, right? Like in CBF-based control, right? So these are all the controllers that keep, all the controls that keep the feasible set safe, no? And then this is the feedback controller that we designed, which is a little bit different than the one that you usually see, right? The one that you usually see is like, you know, minimize control effort, no, subject to the constraints, right? This is not minimize control effort, right? This is minimize perturbation to the gradient, because that's what I want to do, right? I don't want to touch the gradient unless I have to, no, because I'm interested in optimizing the function, right? So I'm going to do, you know, it's still a QP, right? This is still quadratic in U and B, right? It's not control effort I care about, is, you know, perturbation to the gradient, right? And when you close the system, no, when you take that controller, no, and you put it in there, that closed loop dynamical system is what we call the safe gradient flow, right? It's the closest you can be to being gradient in terms of direction, right, while remaining safe. So that's why we call it the safe gradient. And, you know, once you discover something like this, of course, somebody else invented it before you, right? So it turns out that we realize that when you only have equality constraints, not within equality, but only equality constraints, Tanabe, right, back in the 80s, right, had thought of, I mean, with only equality constraints, it's like you are dealing with a manifold, right, like a submanifold of the, and so he thought about, okay, how will I keep the gradient, no, tangent, no, how will I do it, right? So if you take our flow, you know, this flow over here, and you only have H, no, H functions, equalities, you can actually write the solution of this in closed form, right? When you write the solution in closed form and substitute, so then you can write the same gradient flow in closed form, then it ends up being this dynamics over here, right? And that dynamics is in Tanabe's paper. And, you know, again, some other people have rediscovered Tanabe's paper without realizing that they were rediscovering Tanabe's paper, right? So there are recent papers on, you know, kind of machine learning, how to escape local saddle points, blah, 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 that actually are using Tanabe's. So we also realized that was sort of interesting. Okay, so for instance, what is the connection with the projected gradient flow? Or actually, this slide also you can also say as another way of defining the safe gradient flow, right? So what do you do in the projected gradient flow? What we were mentioning before, right? You take the gradient and you project it whenever necessary, right? So actually, you project it at the tangential, no, cone, right, of the constraint set. The tangential cone of the constraint set is when you are in the interior of the set is everything, right? Everything, because, you know, here, when I am in the interior, no matter in which direction I go, right, I will still remain, right, in the set, no, infinitesimally, right? So that's what projected gradient descent does, right? I don't care until I hit the boundary, right? When I hit the boundary, the tangent cone is only the directions that are pointing, no, towards the interior or tangential, right? And the tangent cone is not defined outside, right? Outside is empty, so the projected gradient flow is actually not defined outside, right? Okay, and so this is actually the way that, you know, formally you can define the tangent cone. You know, it has the constraints here, the equality and the inequality. You see this subindex here, this means the ones that are active, right? When you are at that point, right? So here there are non-active, right? No, because it's strictly negative, right? So this, you know, not there, right? Here, well, whatever is the G that corresponds to this line, that's the only one that is active, right? This one is not active, no, at this point, for instance, right? So this has nothing to say, right? When I am at this point, right? That's why the tangent cone is like negative, right? So, okay, we can define another object, which is not a cone, right? But something that we call restricted tangent set, no? Which we define like this, no? So these are the same same equations with the alpha there, right? And those are the same equations with the alpha, but for all the functions, right? For all the functions. Because the alpha is the one that, is gradually taking care of things. So we call this the alpha restricted tangent set. And the good thing about that set is that, first of all, it's defined everywhere, right? When you are in the interior, it kind of has the feeling as the tangent cone, right? You can go in every possible direction, right? But there are some directions in which how much you can go is limited, right? Which is, corresponds to that guy. No? When you are at the boundary, it's exactly the same as the tangent cone, exactly the same, right? Because these directions are gone now, right? And when you are outside, you see this weird thing, right? Where the point at which I am computing that set is not in the set, right? Because, what happens when you're outside, you want to be going back, right? Towards you satisfy the constraint. So this will pull you back, right? Which is actually something good for the shape gradient flow. If you're starting feasible, it wants to, bring you back to feasible, right? Okay, so if the projected gradient flow is defined as the projection of the gradient on the tangent cone, right? How about what is the projection of the gradient on this set, right? And implies the projection of the gradient on that restricted tangent set is the shape gradient flow, right? So the shape gradient flow is also a projection, if you want. It's not over the tangent cone, right? It's over this other set, right? And so this, for instance, gives you also a sense of the connection, right? As you play with that parameter alpha, what we were saying before, right? Bigger and bigger alpha make you less and less worried, right, about the boundary, right? So when you do the limit, you recover the projected gradient flow, right? And so here you have different trajectories for different alphas, right? And so you see, if I start here, with a very small alpha, I'm so worried about the boundary that I start modifying already the flow a lot, right? So you see that this trajectory stays well far away, right, from the boundary. As I increase the alpha, you start seeing trajectories that, are riskier, if you want to call them like that, right, are less worried about getting close to the boundary if they need to. No? This is only if the gradient is taking them there, right? All the way to, when alpha is equal to 10, it already almost looks like what the projected gradient flow will do, right? It will follow the gradient, hit here, get projected, hit here, get projected, all the way to the device. Now, the nice.
What was alpha?
Alpha is this parameter that we.
Okay,
Right. Yeah, exactly. So my class K function is linear. That's the alpha. The interesting thing is that no matter what the alpha, you still always converge to the optimizer, right? So the alpha is, you get to be more or less mindful of safety, right? But convergence to the optimizer is there, right? And we in the paper with Ahmed, we have this thing about the vector fields, right? You can actually say things about the trajectories, not the vector fields, right? But one level down, right? The actual trajectories, and that is something that we've explored with Giannis and Maurice. Kind of came around these similar ideas, at the same time. Okay, turns out that the shape gradient flow also has some nice interpretation in terms of primal dual algorithms. Maybe you can look at the state as an approximation of what the primal variable should be, right? And you can look at the controls U and V as an approximation of what the dual variables, right, will be when you are doing primal dual things. And what can we prove now, right? So, okay, this is the design, right? But what are the properties? And so, well, if you're familiar with optimization, they have all these constraint qualifications, conditions, right? For, you assume that the problem that you're trying to solve is feasible, because otherwise, that's it, right? If it's not feasible, then you are not trying to solve anything, right? But what feasible means can be different things, right? And so, for instance, if we assume this Mangasarian from OH constraint qualification, it has to do with the G's and the A's, right? That the gradients are linearly independent at points in the boundary, things like that, of the active ones. Then we can prove things like, okay, any equilibrium of the shape gradient flow corresponds to a KKT of the optimization, right? So if you if the safe gradient flow goes to an equilibrium, that equilibrium is a solution of what we were trying to solve, right? And then if you ask for a little bit more in terms of constraint qualification, then you can prove that the safe gradient flow is defined in an open set that contains the feasible set, right? Meaning that even if we start outside, it's well defined, right? And it will pull us back. And is better in terms of continuity, right? That the projected gradient descent, right? Is Lipschitz, So it's not only continuous, it's actually Lipschitz. And yeah, you can say more things about properties of this, I guess, that I can skip. Is forward invariant, right? The feasible set is forward invariant by design, I guess, and is also asymptotically stable on that open set, right? What I was saying, right? You will get pulled back, right, towards that. And then in terms of, yeah, exactly, this is what I was saying, right? If it is initially feasible, remains feasible forever. If it is initially infeasible, you want to get exponentially fast, right? Get to satisfy the constraints.
Can I ask something?
Yeah, of course.
So the result on the Lipschitz continuity of the solution, is it for one constraint or for multiple constraints? Okay.
Yeah. Right. Actually, we've learned so much with those things, right? Because we've actually gone crazy. So that's why we wrote this paper, right? Because exactly when you start having more than one constraint, right, it's difficult to determine the continuity properties, right, of what you get, right? Yeah. So, and we were pulling, there is all this literature on parametric optimization. And we were pulling, there is this result in this paper, and then there are these nodes that have this other result. So this paper is not really like a new results paper. It's more like, everything that we've collected, right? Let's put it all together in one paper, right? So that people, so even in this, I guess I don't have it, but we have a table, right? That really tells you, okay, if these conditions are true, then I can say continuous. If these conditions are true, then I can say locally. It's almost like a lookup table of everything we know. I'm sure there are more things to know, but at least the ones that we know, we've collected. And, okay, and they're increasingly, so MFCQ is the ones that I was mentioning before, right? Mangasorian, Afromovich constraint qualification. CRC is the constant rank condition, so we can prove asymptotic stability, relative to the constraint set, to the feasible set. If you ask for a little bit more, you can actually prove asymptotic stability on the open set where the safe gradient flow is defined. And if you ask yet for more, then you can prove exponential stability. And the nice thing is that all these proofs are really Lyapunov proofs, right? For the first one, because it's relative to the constraint set, right? Where the constraints are always satisfied, you can use just the objective function, right? Because you never leave, right? For the second one, because it's, potentially infeasible, right? You can also start infeasible. Then that is not good enough, right? You also need to kind of measure, the constraint not satisfaction, right? In your Lyapunov function. So then for exponential, we have to do like a Jacobian of this thing. And it's tough, right? Because the way we have defined this is the closed loop system of a controller that is defined through an optimization problem. So just computing this thing is not trivial. It's quite not trivial. Then we have versions where, if we start assuming things about the convexity of the objectives and the constraints, then you can prove global things, right? And so you see here, right? If the function is convex and the constraints are convex, then we have global Lyapunov stable. If it is strongly convex, then we have, global asymptotic stability. So there are these versions of the results. We can even prove that if you choose carefully the alpha, if you choose carefully the alpha, then you can also prove that the safe gradient flow is contractive, right? So here I've given you two examples when the alpha is not large enough, right? Here is when it is large enough, And this property of being contracting, is that any two solutions are kind of getting closer to each other, right? And is equivalent to some notion of strong stability, right? This incremental stability property, right? That is really advantageous, especially when you're trying to interconnect these dynamics with something else, right? Because it means that it's very robust, right? When it is contracted. Oh, sorry. So here I have, simple optimization problems, simple constraints, and then just different algorithms, right? Running for this problem. And so I think this is an example like the one we saw before, right? So this is the projected gradient descent, and this is the safe gradient flow, which I think we already saw. This is the typical behavior that you will see with the primal dual, no? Saddle point dynamics, right? You will converge, right? And it's well defined, no? Smooth, right? Even, but it doesn't satisfy the constraints at all times, right? Because it's that oscillatory, and different penalty methods that get also the smoothness and get also that one gets the invariance, right? But don't converge to the exact optimizer, right? Because of the perturbation, right? To make the barrier. Okay, yeah, there is a, you can put this in a slightly bigger context. A constraint optimization problem is a particular example of a variational inequality. No, if you work with games and things like that, I'm sure you've come across variational inequalities. A variational inequality is something as simple as that equation over there, right? It's just a point, no, that satisfies that constraint, right, for all other points inside the set. So those are the two things that you need to define a variational inequality: set and a map, right? No? But the good thing about variational inequalities is that they encode many problems, right? Like finding the zeros of a function, right? Finding a constraint, the solution to a constraint optimization problem, right? It's also variational inequality. Finding saddle point, right? Being max, no, it corresponds to this, this function f there, and those constraints. Even solving, finding Nash equilibrium, right? When you do this, what people call the pseudo gradient, right? With the cost functions, right? Those are the ones that you put in the capital F, and here you put, the sets, right? So we've done this, no? But everything we've done, you can really do it more generally for variational inequalities, and so we've defined something that we call the safe monotone flow, which is basically following the same recipe, right? Just to go. Okay, so this is an example just to show you a little bit, right? Just to test drive, I guess, no? This idea of the safe monotone flow, right? And so here I have an LTI system with like this, right? And I'm thinking of two players, no? The first player chooses this signal, and the second player chooses that signal, right? So they are playing a game, right? And this is the payoff function, no? So the first, you see that, the game has to do with the final state, right? Of the LTI, no? This is, I guess, the transient. This is the control effort of the first player, and this is the control effort with a minus of the second player, right? So the first player wants to minimize this thing, right? Just to keep the system stable, right, or at least bounded, minimizing its effort, right? The second player instead wants to maximize this thing, right? Wants to destabilize and also minimize its. And if you put constraints on the, this is a MPC kind of problem, right? That you can solve well, easily, I think, right? If you don't have constraints, right, on the signals, right? If you just choose whatever, right? But as soon as you start putting constraints, very simple constraints, then now numerically it becomes much more involved, right? So I guess these are the objectives that I was mentioning, right? The first one wants to minimize, the second one wants to maximize. So here I show you, I think, right, different simulations where, I guess, I'm solving this in a receding horizon fashion, right? So, there is this time, I solve this thing and implement the first one, right? Then we go to the next one, solve it again, right? So you see that there are two processes, right? There is the LTI system, the plant, right? And then there is the solver, right? For the, what should I do? What should I do, right? So here you see in the, if I have TF equal to infinity corresponds to, I have an unlimited amount of time, right? So I will solve this, exactly, right? And that I will implement, in the LTI system, right? The first one, right? And then I go to the next time step and do so, right? And so if I do that, then I get, the black curve here and the, this red and something, right? I think it's, this one, or maybe it's this one over here. I cannot see it. You can see it here better, right? And then, you know, if instead, if I use the safe gradient flow, right, to solve this problem, right, then, but I don't give it enough time, right? So I give it, sometimes I give it 10 seconds, sometimes I give it 5, 2, or 1, right? So it's like, I'm trying to solve this optimization, but after, you know, let's say 10 seconds, whatever solution I have, I implement, right? Whatever solution I have might not be the optimal, but it surely has to satisfy the constraints, right? Because this is what the players can do, right? They cannot do negative, no, for instance. And so that would be the problem if I was using something like primal dual, right? Where if it didn't have enough time to converge, maybe the current estimate says do something negative or something like that, right? And so this is what you will get, no? The other curves is the ones that you will get with the same gradient flow, right? The longer you give, right, the closer you get, right, to what you will do if you have infinite time, right, to solve things. But at all times, everything is feasible, right? So you can actually implement it, right? That's kind of the... Okay, somebody might say, well, I define the safe gradient flow in 2 ways, right? One was as a control problem, another one was as a projection, right? As a control problem, I still need to solve, it's funny because it's a flow that I have defined to solve an optimization problem, right? But to find the controllers, no, to find the flow, I still need to solve another optimization problem, right? Which is this one. I mean, you could argue, well, it's a QP, right? So not that big of a deal. But if you really say, no, it's a big of a deal, right? So you know, this is an optimization problem. How will I actually solve it? Well, okay, it's an optimization problem. So you could actually try to solve that constraint optimization problem. You could actually try to solve it with another safe gradient flow, right? Now the one for that problem, right? And so it turns out that that one you can write in closed form, right? Yeah, and so it takes this form over here, right? So, you know, this thing, no, is that dynamics over there, right? For which we want to find U and B ideally in this way, right? But this is an optimization itself. So I can write, no, again, the dynamics, right? To solve this optimization. What dynamics do I write? The safe gradient flow, no, for that optimization. And I actually can write it in closed form, right? So this is what we call the recursive safe gradient flow. Doesn't require solving any optimization at all. It's just that I'm not exactly doing the same gradient flow because, again, these dynamics might not have enough time to solve this exactly, right? No, same. But, you know, you can prove things like practical safety and things like that. I think this is what I have here, but I think this part I will skip. Okay, you might say, well, in optimization, we care about discrete time, no, rather than continuous time. Everything I've discussed is continuous time. So we've started, I guess, to look at discretizations, right, of the safe gradient flow. On the positive side, you know, it's a first-order method. We have Lyapunov proofs for everything, right? So it's going to work out for sure, right? It's just a matter of writing things carefully, right? I mean, there are 2 things to work out, right? There is the stability or convergence properties, but there is also the safety, right? So we know that it's going to work out on the convergence side because that's what we see with standard gradient, right? We have the objective function and that works. No? How about the safety? Well, I mean, the same way that things work well with convergence, right? Because of the sort of like the ISS properties, right? Of gradient flows, right? That they are input to state stable, right? It should work well with safety, you know, if you think of ISSF, right? So input to state safety, right? And so that's, you know, I mean, we have some results to show that, right? And so, for instance, one thing we've realized is that when you do like a very simple discretization of the safe gradient flow, then you can actually rewrite that discretization in this way, right? Which is something that, you know, people working in sequential convex programming do a lot, right? These kind of things, right? Where you are optimizing something, convexify the problem around the operating point, solve an optimization problem itself there to find the direction, and then go there and then redo, right? All of this. And that connection has allowed us to, you know, in some cases, right, when the feasible set is polyhedral, we can actually tell you, you know, how small should the step size be, right? And this is a function of the alpha parameter that you get to choose. and also as a function of the Lipschitz constant of the gradient of the objective function, right? So if you choose those things small enough, then you can actually still guarantee the right things, right? That, you know, even though you are discretizing this flow, I mean, when you discretize, then you run the risk, no, of taking, even if your direction is correct, right, taking too big a step, right, so that you actually violate safety or you pass, no, the critical point. Well, we can actually, you know, specify, you know, how small should the step size be so that you don't, you know, potentially not interesting things. But there is still more to, I mean, much more. We are just scrapping the surface. Here, just to give you a sense, you know, if you think about what we were discussing before, right? The alpha parameter, right? Alpha very large is like, I don't care too much about the boundary, right? So I think, you know, alpha very large goes well with very small step size, right? Because the alpha very large allows me to get very, very close to the boundary, right? So the step size should really be very small, right? And instead, alpha small should allow for a kind of a larger step size, right? And so you see this in this plot, right? From left to right is increasing step size, right? And from top to bottom is increasing alpha, right? And so here, I guess, is the smaller alpha, right, at the top row, no? And so you see that, you know, for still bigger and bigger and bigger H's, right, only when the H is, you know, the largest, no, that I plotted here is where we see, you know, safety failure, right, that property, no, of informal invariance, right? Up until this value, no, even the discretization remains safe at all times, right? As I do the alpha bigger, right, you know, for this H still works, for this H still works, for this one, no, it doesn't work anymore, right? When I make alpha even bigger, even for this H, it doesn't work anymore, right? So there is this, you know, connection between the step size and the alpha, no, which, you know, is sort of captured here, right? That the H goes like the inverse, right, of the alpha, right? The bigger the alpha, the smaller the step size, no? Which, you know, matches the intuition, I guess. So, okay. We've also been trying to use the safe gradient flow now with the original motivation that I mentioned at the beginning, right? That, you know, we want to hook it up with something, right? So I'll tell you just a little bit about that. But in general, you know, every time you want to solve some constraint optimization problem and you want to do it in a sort of like anytime fashion, right? You could use. And so we've used it in voltage control for distribution networks. Recently, in a paper we submitted to L4DC, we've done it for safe reinforcement learning. We haven't, but other people have used it for extreme seeking, and I'll tell you a little bit about that. And then, yeah, we've done it also for online feedback. So, yeah, I have 5 minutes, no, Basilio?
Yes, more actually, 7 minutes.
Oh, 7. Okay. So for instance, in you know, in voltage control of distribution networks, you are interested in you know, keeping the voltage within some limits, right? Upper and lower, right? You don't want the voltage to go, no, beyond those limits. And you know, typically you are operating on these you know, power flow equation solutions, which are, you know, the network is stable, right? The demand for this demand that, let's assume, is settled, right? Is that demand, right? Then, you know, these are kind of the operating points, right, of all the distributed energy resources that you have in your network. Now, the problem is that, you know, the demand is not predictable, right? And sometimes you don't know what the demand is for many reasons, right? Because you have renewable integration in your network. Because, you know, maybe there's EV charging, all of those things, right, create voltage deviation. So you have a need to constantly, really, you know, being adjusting, you know, those power injections to keep the thing, right, operating optimally, right, and with those voltage constraint limitations, right? You don't want to violate it. So, you know, Landran and, you know, her group have done a lot of work there where you try to optimize the transient, you know, as things move around, or also you try to optimize the steady state. In this paper, we were kind of combining both, and maybe the details are not that relevant. But, you know, the key thing here is that, they eventually end up training a neural network here, I think, right? So that this determines the Q are the reactive power injections, right? What you're gonna do so that these voltages, remain in this limit. And the way I guess we wanted to solve this optimization problem was in such a way that we never violated, right, the limits. And so for that, essentially, we used a version of the same gradient flow. And so, quite successful in terms of the performance and the fact that we get quite good. So the other example is this one for the C paper, right? And so, just formulating a safe reinforcement learning problem like this, right? You have the value function, for your objective, and somehow you encode constraint with a different value function, right? You see that, they look like the same, it's just that the rewards are different, right? They have a reward for the objective, I have a different reward for the safety. And so basically, I guess, as you are doing reinforcement learning, right, to solve this thing, you want to do it in a way that, satisfy the constraints at all times, right? It's like, somebody drops you in an environment and I don't know where the chairs are and everything, right? I want to sort of explore, I want to get to the door, right? But I want to do it safely as I'm doing it, right? I don't want to. Now, it's a little bit problematic, right? Because actually, because I don't know where the environment, the problems are, I sort of need to get close to the problems, right? So that I know where they are. So, but okay. So I guess, the way you can encode this is you can say, well, I'm going to try to run the safe gradient flow, right? That's the objective. This is the constraint, right? And, this is that version, this discrete time version that I was showing you before, right? Of the safe gradient flow. No, and what we can prove, and I think what we prove in that paper is this idea, right? That, if we have a parameter in your policy, right? So this gives rise to a policy, right? Right now, we are optimizing the policy, right? So if that parameter corresponds to a safe policy, then, we can ensure that the next policy, right? The one that we are obtaining as we keep learning more, right? Will still be safe. And okay, this is not a deterministic guarantee, right? It's with some probability, and that's a tunable probability, right? So we can make it arbitrarily high if you increase the number of episodes, right? Because we are estimating, the value function and the gradient. We can also, the property that we mentioned about the safe gradient flow, right? Even if it is unsafe, right? So even if it is infeasible, right? Then we can find a bound on the number of episodes that we need to consider so that at the next time, right, the next policy will be safe, right, with, again, some prescribed high probability, right? And the higher you want this, well, the higher the number of episodes you do. And then, you also have convergence, right? So eventually you run this long enough, right? Then you will have a, something that solves that optimization problem. And so here, for instance, is an example of the safe gradient flow in practice, right? We start here. I think these are 4 different initial conditions, right? And this is a policy. I don't know. I should have written here the time steps, but early, right? Like at the beginning. We are still checking things, right? And as we keep running it for longer and longer, right? Then we get a better and better close to optimality, right? And you see that at all times these things remain safe. I guess because we've run it with enough number of episodes, And so just to give you a sense, right here, when we run it here, this is the evolution of the value function, right? Or the estimate of the value function. And this is the number of times that we estimate that we are unsafe, right? Across how many, 10,000 it looks like, 10,000 iterations, right? So out of 10,000 iterations, we are unsafe 120 times, right? If we run it with 300 episodes, right, per iteration. As you start increasing the number of episodes that you consider, all your estimates get better, right? So you see that the number of times that, this becomes unsafe, increases, right, substantially. And so that's consistent with what I was telling you, right? With a prescribed high probability that depends on the number of episodes. And we haven't done anything fancy in building those estimates, right? The estimators of the gradients, of the value function, anything. So I think that if we were to do something better, these things will, will become much smaller, right? So this is just the first example. Now, something that we haven't done is doing, in extremum seeking, you are interested in solving problems like this where you don't know the J and you don't know the H, right? you don't actually have expressions for those, right? What you can do is you can try some value theta, right? And measure the value of the objective function or measure the value of the constraint, right? And so in extremum seeking, you sort of do this kind of sinusoidal excitation, right? Just to, basically, if you want to know the gradient of a function here and you measure the value of the function around, right? Well, then you kind of start getting a sense, right, of how the gradient looks like, right? And so Miroslav Kristich and his group, we came across these papers that actually, when we realized that what they have been doing is actually they have been implementing the safe gradient flow or their version of their safe gradient flow, right? It's an objective function with one constraint here, right? So, I thought that was cool. And actually, they have also implemented it in the particle accelerator at Los Alamos National Lab, right? Because there, when you are trying to, I think it's the beam, right? The beam size. When you are trying to tune the beam size, you don't quite know because of the complex physics, right? Neither the value of the objective function nor the value of the safety. We've done it also more. Maybe I can skip, I think, right? Because I'm already past. But we've done also some papers where we do really the interconnection, right? There is sample and dynamics, in this case, a power network, no? And there is, optimal set points for the DRs, right? And those optimal set points are gonna be determined with the safe gradient flow, right? And so, very, very interesting results. So I think that's all I had. There are many things still we wanna do, right? More online learning, I think, because this anytime property, is interesting. The connection definitely. Because we are doing the discretizations, more understanding, right? I would love to have a statement that says, the safe gradient flow is ISS or something like that, right? Or the safe gradient flow is ISSF, right? Under such and such properties, right? And I think we are close, but not there yet. Yeah, so that's it. So the first two at the top are really the safe gradient flow things, right? And all you guys are just okay. Let's use it for some, right? So the ones that I was mentioning.
So let's take a couple of questions, and then we can do also client questions, so we can let people go if they need to.
Or like on picture, pick up
Yes.
and then you can.
Is there any benefits using congestion information like Newtonian type version of and what is the benefit?
Well, I think there would be a second order information speeds things up, right? So yeah, that will be the benefit. It's just that I would like to, I don't know how to do it, but definitely, there will be. It will speed things up.
Let's go with James.
Excellent talk. I had a question about the monotone flow. So when you use the VIs, you've essentially leveraged the monotonicity of the operator. But when you did in the optimization setting, the equivalent VI operator would have been non-monotone because you didn't assume any convexity of error.
That's correct. So the monotone, the VI case, we only do it for the monotone.
Yeah,
right?
so I'm curious, do you think that the non-monotone regime is within reach?
See, that's a great question. I think so. Yeah, that's a great question. Yeah, I would say yes, but that's a good point.
And I will do Gabor and then also one more question. Yeah, Gabor, go.
This is a follow-up on Jeff's question. So, I really like the story you told us because it kind of took a topic which I'm always a little careful about, optimization. I don't quite really understand what's going on, right? To a topic which I really love, which is continuous time dynamical systems with all the geometry in it. One thing which, however, you did in the examples, at least that you showed, is that you had kind of one global equilibrium which you were trying to get to, right? And my understanding in many of the optimization problems, especially people are solving in machine learning, one of the challenge for them, they have a lot of local optima and there are saddles and so on. So maybe on that, like Hessian could help, right? Because if I'm close to a saddle, it would be nice to not to go there, right? And all those things. So
That's the other, yeah, that's a good point. Yeah, very true, very true. Yeah.
Well, let's do one more question and then we'll take the rest of the time. So, I'm wondering how this would change if you have uncertainty in maybe where your agent goes after you perform some adjustment, like if you would want to model that with like an SDE instead of just a differential equation.
I see.
Stochastic.
It's a great point. Yeah, you could do like a stochastic version. Yeah. I guess I should add that to the outro. Yes, like an SDE version, right? Of the, yeah, I think that's a great. I mean, be done.
Let's forget about
I won't be there for the entire.
Days, my friends, retirement. Yeah. Well, yeah.